Hi, this is Gary Rubenstein. This is part 3 of a series of videos where I'm taking kids and parents from kindergarten through 11th grade math. And it's just some things that I've been thinking about math since I'm a small child, and I've been teaching it for a very long time. And I teach high school math, but I've taught middle school math, and I have kids who are in elementary and middle school. So I think about this a lot. And maybe some of my insights will help some kids and some parents. Last video I was talking about maybe 3rd grade, multiplication, times tables, maybe going into 4th grade. I want to say a little bit more about multiplication before we get into division. One use of multiplication is in geometry, finding the area. So when I say something like, what's 5 times 3, that's also the area of a rectangle that has 5 and 3 as its length and width. So when we say 5 times 3 is 15, that 15 is also the area of this rectangle. We can see that there are 15 squares, units in this rectangle. Well, that area model gives a nice way to understand a question I was looking at in the previous video, which was multiplying 24 times 53. Here's 24 times 53 using sort of the old school multiplication process. And I'm going to compare it to a similar way of thinking about it using what's called the area model. In fact, I think I'll show you the area model first. If I were to make a rectangle that was 24 by 53. The area of this rectangle would be the product 24 times 53. Now, let's say I don't know how to multiply 24 times 53. I don't know an algorithm for it. Well, check this out. If I split this 24 into 20 and 4, and the 53 I split into 50 and 3. All I did was put a line there. I'm even going to erase. Just going to put this line here separating the 20 from the 4 and the 50 from the 3. Well, the area of this big rectangle has not changed just because I stuck a line here between 20 and 4 and 50 and 3. But these two markings allow me, if I draw a horizontal line here and a vertical line here, it lets me split up that rectangle into 4 rectangles. And if I can get the area of each of those rectangles individually, the sum of them will be the answer. Well, the easiest of the rectangles is this red one. It's just 4 times 3. If I know my times tables, I know that little red rectangle is 12. Now, the green one is 4 times 50. But 4 times 50 is kind of like 4 times 5, and then that thing times 10. So since 4 times 5 is 20, 4 times 50 is 200. This blue rectangle is 3 by 20. So it's going to be 60. And this big yellow rectangle is 50 times 20, which is 1,000. And if I add those 4 things together, 1,000 plus 200 plus 60 plus 12, I get 1,272, which is the answer to 24 times 53. These four answers, we could actually do them in a sort of, this isn't the standard process, but I could do the same idea. Those four multiplications, which were 4 times 3, 4 times 5, really 4 times 50, but it's like 4 times 5, 3 times 2, which was like the 60, and 5 times 2, which was like the 10 that became the 1,000. So I could actually do those four multiplications. First I do 4 times 3 is 12. Then I can do 2 times 3, but 2 times 3 is 6, but it's not really 2 times 3, it's really 20 times 3. So I can say 60. Then I can say this 4 times 5 is 20, but it's not really 4 times 5 because that 5 is really represents 50. So 4 times 50 is 200. And finally, 2 times 5, well, that's 10, but it's not really 2 and 5. It's really 20 times 50. So the answer is not 10, but it's 10 times 10 times 10, which is 1,000. And if this were the multiplication algorithm, where we have these sort of 4 lines, people might, have a better feel for, what they're doing and why it works. But that's not, the modern way only has 2 lines in it. We do 4 times 3 is 12, carry the 1. 2 times 3 is 6, plus 1 is 7. That 72 is basically these two things together. Then they put a 0 here. And they do 4 times 5 is 20, carry the 2. 2 times 5 is 10, plus the 2 is 12. Oops, when I said 4 times 5 is 20, I forgot to put a 0 there. And then I put the 2 up here. 2 times 5 is 10, plus 2 is 12. That 1,200 is really these two guys together. And then we add them together to get the answer. But really, maybe it would all make more sense if we thought about this area model. And this is going to come up like way later in like 9th grade, 8th grade in algebra. This area model is going to come back. But I just wanted to show you that this more lengthy multiplication algorithm that has 4 lines here might make it easier to understand than this 2-line one that has the little tiny 1 here and the 2 up here. It gets kind of confusing. Now, the opposite of addition is subtraction. And you might say, well, that means the opposite of multiplication, division. That's sort of true, but another opposite of multiplication is called factoring. In other words, if I know that 3 times 2 is 6, that's multiplication. If I go backwards and I say 6 is what times what? Well, there's more than one answer, but one of the answers is 3 times 2. When we do that, it's called factoring. And we say the factors of 6, well, 3 and 2 are 2 of the factors of 6. But, we could also write 6 as 1 times 6. So we also have 1 and 6. So there's 4 factors of 6. And finding the factors of a number is a really important thing. Some numbers, like you take something like 12, you could write it as 12 times 1, or 2 times 6, or 3 times 4. Sometimes in younger grades, they say make rectangles that have area of 12. How many ways can you do it? Sometimes you give students 12 little squares, these manipulatives, and you say, can you arrange them into rectangles? How many ways can you do that? And there's 3 ways. We don't count. If we make a 4 by 3 one, we treat that as the same rectangle because it doesn't really give us any new factors. But that is a good thing you could do just by cutting out some squares and say try to make rectangles. If you try to make 12 and you were to try to put 5 squares across, maybe you can make another row, but then you'd have these extra 2 guys sticking out. It wouldn't be a rectangle anymore. So 5 is not a factor of 12. So when you ask someone something like, is 3 a factor of 12, that's another way of saying that is, can you make a rectangle with 12 squares so that like one of the side lengths is 3? And the answer is yes. So finding factors of numbers is an interesting thing, and some numbers have very few factors. What's funny about factors is that 6, the factors are 1, 2, 3, and 6. And when you get bigger numbers, like 7, you might think bigger number has more factors because it's a bigger number. There's maybe more things that can go into it. But 7 only has 2 factors, and 8 has 4 factors again. But 9 only has 3 factors, and 10 is back up to 4 factors. That's kind of interesting. 12 has a lot of factors, like almost all the numbers. I shouldn't say almost all the numbers, but a lot of numbers. 6, 12, 1, 2, 3, 4, 5. So half the numbers from 1 to 12 are factors of 12. Sometimes there's only 2 factors. They can't be less than 2 factors because in the worst case scenario, every single one of these has a 1 and the number in it. So the least number of factors you could ever have is 2. Just if you wanted to give a definition there, a number like 7 is called prime if it only has 2 factors, whereas all these other numbers are not prime. They're called composite. Anyway, students don't have to know those words, but just telling you. So factors is an important thing, finding factors of numbers. And it's a good way to practice your once you know your times tables really well. And you might notice, wow, 2 times 9 is 18, but 3 times 6 is also 18. And you start going backwards and saying, okay, 18 equals what times what? And is there more than one answer? In this case, 2 times 9, 3 times 6. Are there any others? Well, I could do 18 times 1. And that's kind of a fun thing. There's a lot of games that involve factors. My favorite one is this one. This game is so great. It's called the 6x6 product game. We only need one game board, but you can download this thing. It's all over the place. 6x6 product game. And it's kind of like tic-tac-toe. You see over here I have a 6x6 square, 36 little squares. But the numbers, it starts off 1 through 10, but then it skips 11, and it skips 13, and it skips 17 and 19. It actually skips the prime numbers. And the way the game works is you have these down here, you have 1 through 9. And you have these 2, what we call counters. And you put, or just like 2 slips of paper. And let's say I want to put my X onto the 18. So I have to put the 2 counters onto 2 numbers that make 18. Maybe I go with 2 and 9. I put them. And then I'll do it with colors. I put the 18 here. Now, the next player can only move. So since 2 times 9 is 18, we get to put something on. We get to mark the 18. You put an X and an O. You can put their initial. Now, the second player can't just go anywhere they want because they're only allowed to move one of the 2 things. So let's say I decide, I want to go on to this number 30. Well, I'm not going to be able to because I have to keep either the 9 or the 2 as one of the factors. So I have to deal with just multiples of 9 or multiples of 2. I'm going to say, okay, I want to go on to this 16. So I move this 9 onto the 8. Now the next player can't just go anywhere he wants because you have You have to keep one of those, either the 8 or the 2. And you also can't go in a place that's already happened. So he decides he wants to go onto this 8 here, which he can do by moving this 2 onto the 1. Now this blue guy is getting nervous because he sees that the red's starting to build something. So he says, I'm going to move, you can move both counters onto the same thing. So he moves them both onto the 1. That allows him to sort of block what's going on here. Anyway, it's got to be one of the best games I've ever seen for this, because you have to be thinking, okay, I really want to go to 30, or I want to block this 30, so I'm going to have to, or my opponent maybe needs 48 to win, so I'm going to try to avoid 6 and 8, because 6 times 8 is 48. So, and he's going to try to get the 48 by, like, maybe on his next move. I skipped a move, but maybe on his next move, maybe he moves on to the 6 and puts his thing there. And now this guy has to block by moving this onto the 8, which makes it the 48. Oh, the goal is to get 4 in a row, not 3 in a row like tic-tac-toe. Okay, I just wanted to show you that. It's a cool game. Another neat sort of game that I see is something like this. It's been a long time since I've seen these, but they're called like maybe number tiles or math tiles, and the idea is that you have 10 tiles, like floor tiles, little pieces of them, 0 through 9. And like a jigsaw puzzle, there's going to be 10 spaces here. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But you can only use each number once. And I'm looking at this now, it's pretty hard. Like, I'm guessing since 4 times, I have to put 4 times 6, because that's the only thing that ends in 4, if I'm right. 4 times 2 is 4, then I could put a 0 there. But it's probably going to be 6 and 2, so that uses up 2 of the numbers. Something plus 8 is 1 something. That could be a lot of things. It can be 2 plus 8, but the 2 is already being used, 3 plus 8. Anyway, this is pretty challenging. I'm not going to go through the whole thing now, but that's a fun challenge. And there are hundreds and hundreds of pages of these that go through different levels. So that's like a little activity. You can just make it. You could download the sheets, and then you can make your tiles. I did it a little here. I ran into a dead end because my numbers left. I'm not able to fix this. I realize these 2 numbers this number has to be pretty small. So when I subtract away something small from it, I end up with something small. So I'd have to mess around with this some more. See, it's pretty fun even for me. One nice use of multiplication is like proportional reasoning. Like if I say there's a recipe that takes 4 cups of sugar and 6 cups of milk, the idea that, okay, what if I want to make, and that serves, 2 people can have that. You say, well, what if I want to serve 4 people? And the idea that, I have to that's double the amount of people. So I'm going to have to double the recipe. And that idea of like everything needs to double, that's a real important thing. We say things like, if 5, packs of, Pokemon cards cost $20, how much would 10 packs cost? How much would 1 pack cost? That idea, and that's a division, but still, the idea of multiplication for sort of scaling something up, that's an important concept that's worth introducing when you start doing multiplication. So we're 2.5 videos into this series, and really, if my kids in third grade, which my own child just finished third grade, if they were able to do all the stuff we've done so far with adding, subtracting, and multiplying and factors, yes, you want to have some pattern finding and maybe some stuff with shapes just to get comfortable with those. But I would be pretty pleased if my child knows all that stuff by third grade. In fourth grade, the big concept is division. And I want to say a couple of things here about division. When you say something like 10 divided by 2 equals 5. So these three numbers, 10, 2, and 5, have a relationship. You know, we can take those three numbers and say 2 times 5 equals 10. 10 divided by 5 equals 2. 10 divided by 2 equals 5. You can make these three equations out of using the numbers 10, 5. Yeah, that reminds me, there was a game. It was a great game. It was called the 24 game. I'm going to have to look up what that, how that worked. There were like these cards, and the goal was to achieve the number 24. Let me see if I could find one of those cards for you. Hold on. Here's one. So basically you have these four numbers, and the goal is to create an equation using the four numbers so that you achieve 24 as the answer. And in this case, I guess you could just multiply them all together. But there's other times where you have to like multiply and subtract. And that's a famous game. You buy like a deck of cards for like $10. Keeps people busy for a long time, and it gets them like just thinking and getting comfortable with numbers, because if you're not comfortable with numbers, you're not going to be able to do the more advanced math if you're stuck on just the numbers. Just like if you can't read basic words, you're not going to be able to read classic literature. So I see kindergarten through fourth grade as getting comfortable with the basic math operations and sort of being able to manipulate numbers. Okay, I want to say a little more. I want to talk about division now. If I told you to create a division problem to model 10 divided by 2 equals 5, and I said it's got to be a division problem that involves cookies, most people would probably say you have 10 cookies and 2 kids. How many cookies? And you want to give each kid the same amount of cookies. So how many cookies should each get? Most people think of that as the one and only question that you can ask. So here are the cookies: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maybe they're chocolate chip cookies. And most people think, okay, 10 divided by 2. I have 10, and I'm cutting it into 2 equal pieces, and each piece is 5. Well, that's true. And that is one question you could ask that involves cook 10 cookies and the division question, 10 divided by 2 equals 5. But there's another question that you could ask with 10 cookies and 10 divided by 2 equals 5. And it's real important because most of the time in math, when you're doing division, I shouldn't say most of the time, but some of the time, it's this other conception of division. So I'm going to go back here, and I'll still have the 10 cookies. But the other question is, I have 10 cookies, and I want to give 2 cookies to each child. And the question is, how many children can I give the cookies to? So that one, the picture would look more like this. 2 to this kid, 2 to this kid, 2 to this kid, 2 to this kid, and 2 to this kid. And it's still, the answer is still 5. But it's a different way of thinking about it. See, that first way was thinking, 2 times, what number times 2 equals 10, basically. I guess the second one's thinking of it that way also. But they're a little bit different in their conception. One was splitting 10 into 2 equal pieces, and the other was splitting 10 into pieces that were size 2 and seeing how many pieces you get. You might say, well, I like to think of it the first way, because that's how I think of 10 divided by 2. I take 10 and chop it into 2 pieces, 2 equal pieces. But the reason this other way is important is because it helps us understand how to do the dreaded long division, which is what I'm working up to here. When you do 10 divided by 2, if 2 is a factor of 10, and you know your times tables really well, remember from before, like what are the ways of multiplying 10? Multiplying to get 10? Well, one of them is 2 times 5. So if I do 10 divided by 2 and I know that one way of writing 10 is 2 times 5, well then the answer is 5. Or if I do 12 divided by 3, I think, well, since 12 is 3 times 4, I can divide 12 divided by 3 is 4. So knowing the times tables is good, but an idea that a lot of people probably forgot is that division, just the way multiplication, 2 times 5 is 2 plus 2 plus 2 plus 2 plus 2 equals 10, 5 2s. Well, 10 divided by 2, if I think of it as this way, we're asking how many 2s fit in 10. And when we think of it that way, it becomes related to subtraction. So if you know how to subtract, you can do 10 minus 2. You can kind of count. I've taken away 1, 2, but I still have stuff left. I have a remainder. And I keep taking away 2. Until I have nothing left, if it goes in evenly. And the answer is 5 that way. So just as multiplication is related to addition, division, only if you're thinking of division in this way. If you think of it in the other way, it's not really subtraction anymore. It's like you can still get the right answer that other way, splitting 10 into 2 equal pieces. In that way, we're thinking of it as like the opposite of multiplication. But this other way is related to repeated subtraction. So you can do any multiplication, even if there was a remainder, you could say 12 divided by 5, and if you do 12 minus 5 is 7, and then minus 5 again is 2, you would see that we took away 2 different 5s, and this 2 that's left is, we call it the remainder. There's 12 cookies, trying to give 5 cookies to each person. I can give to 2 kids, but there'd be 2 cookies left over. But this idea of division being related to subtraction will help us understand the dreaded long division, which again I'm working towards. If you're dividing, a fairly small number by a factor of it, well, then it's good if you just know if you know the times tables. 24 divided by 8 equals 3. If it doesn't go in evenly, like 25 divided by 6, well, we say, if I'm giving 6 cookies to each person, I can only give to 4 people, but it doesn't go in evenly. So here we say, we put the 24 there. That is equivalent, when I do 4 times 6 is 24 and subtract 1 and get remainder 1. That's the same thing you would get if you went 25 minus 6 equals 19, minus 6 equals 13, minus 6 equals 7, minus 6 equals 1. And you said, okay, well, I took away 1, 2, 3, 4 sixes. That's where the 4 came from. And this cookie that's left over would be the remainder. But we don't, yes, you could subtract over and over. But what we end up doing, instead of subtracting 6, 6, 6, 6 over and over, we say, well, why don't I just subtract all 4 sixes at once? And that's where this 24 comes from. That's saying I'm subtracting that thing is 4 times 6. So when I subtract them all, I end up at this 1 right away. And that's what happens in division with remainders. But this gets more complicated, so I'm going to take a look now. What if instead of dividing 25 by 6, I were to divide 253 by 6? Okay, so that 253 is a large number, and there's no way you're going to want to do this. But in theory, you could. See, this is more like the taking away 2 cookies at a time thing and not the splitting 253 into 6 equal pieces. If I had a lot of time on my hands, I could subtract 6 over and over, and I could count up how many 6s I subtracted. I'd get my answer. But that would be crazy. That would take too long. It's obviously a lot of 6s that go into 253. What if instead of taking away 6s, I took away 6 Ds? That would be better. That would save me a lot of time. Because what I would do, let me move this over here. So a concept that's really clever is I don't need to take away 1 6 at a time. I could take away 10 6s at a time. Take away another 10 6s. Take away another 10 6s. Take away another 10 6s. And at this point, I've taken away 10, 20, 30, 40 6s, because that was 10 6s, 10, 10, 10. I've taken away altogether 40 6s. But I still have some cookies left over. So I have 13. So now I start taking away regular 6s. And I ended up taking away 2 more 6s. So I've taken away 42 6s altogether, and I still have a cookie left over, remainder 1. So you could do that, or you could do the trick, long division, where you basically model this process. You ignore the 3 at first. You say, okay, 25, which is basically like 250. 250 divided by 6 is kind of like 25 divided by 6, but it would be 10 times as many. So 25 divided by 6 is 4, remainder something. So 250 divided by 6 is 40 something, and that's why the 4 goes here in the tens place. That 4 is basically saying this. And when I put this 24 here, which I'm actually going to do something a little fancy, I'm going to put 240. Because that 4 means I've taken away 40 sixes. 4 times 6 is 24. 40 times 6 is 240. And then when I subtract and get 13, I'm already at this point right there. So the answer is not 40, because there's still 13 cookies left. So now I do 6 into 13. So now, sorry, I say you go 6 into 13 rather than subtract 6 and 6. We just say, well, 6 times 2 is 12. That's pretty close to 13. And then I subtract away the 12, and I get remainder 1. So this is the dreaded long division. And I just wanted to show you this little progression of like, yes, you could subtract 6 42 times. That would take a long time. Or you could subtract 64 times and then take away 6 2 times. That wouldn't really take that long. But the long division process, oh, and of course, in actual long division, they don't write this little 0 here. But it's kind of implied in there. In actual long division, you do 25 minus 24 is 1, and then you bring down the 3. Let me show that from scratch. Just do it right over here. Six times 4 is 24, but that's really 6 times 40 is 240. But instead of writing the 0, you subtract and bring down the 3. Well, that bringing down the 3 is because you're not really doing 25 minus 24 and bringing down the 3. You're really doing 253 minus 240. And then the 2 and remainder 1. So long division is sort of known as like the thing that makes people, really, really nervous. Even adults, if you had to split a $250 meal among 4 people and you needed to like do long division, it would probably make you a little bit nervous. $62. There's going to be $2 left over for the people to split. They could each pay 50 cents. Anyway, so there's your dreaded long division. And I'm going to say one last thing about division. Even for the 253. A sneaky trick I'm going to put up the regular long division. Is this. Instead of, if you do 6 into 25, you get that 4. But if instead of writing this 24 here and subtracting and bringing down the 3, if this number outside here is small, in this case it's, by small I mean like less than 10, you say, well, 6 times 4 is 24. That's just 1 away from 6. So rather than have the 1 all the way down here and bringing the 3 to it, you could also put the 1 right there. When I was a kid, they called this short division. Short division is when you bring the remainder up. Instead of bringing the 3 down to the remainder, you bring the remainder up to the 3. Then 6 into 13 is 2. And again, 6 times 2 is 12, so there's remainder of 1. Anyway, I like that short division. That's what I would do in real life if there were 5 people splitting a $287 bill. I'd say 5. 5 times 5 is 25. That's 3 away from 28. 5 into 37 is 7. 7 times 5 is 35. Remainder 2. So about $57 each. Okay, well, that's what I wanted to show you. There's a lot more that goes on in math than just adding, subtracting, multiplying, and dividing. But they are really important, sort of the building blocks for everything else. And I just wanted to show you, because really by 4th grade, a lot of students have already given up on the idea of understanding why the math works. And it just becomes a bunch of memorized steps. Some people say, well, they're going to have calculators, so they don't even need to know how to do long division. But there are some concepts that come up in long division and that relate to more advanced math. And long division itself is a bit of like a distributive property thing. It's kind of like, instead of 253 divided by 6, it's kind of like 240 plus 13 divided by 6. And we divide each sort of piece by 6. So 240 divided by 6 plus 13 divided by 6. Well, 240 went in even, 6 went into 240 evenly. But the 13 divided by 6 was the 2 remainder 1. So this whole like distributive property, which also relates, remember in the beginning of this video, I showed you the area model for multiplication. This one. These ideas, when eventually we start, instead of using numbers, we start using like x plus y and z, to make it more abstract. Same ideas come in, but just without numbers. Well, that's a pretty hefty lesson to get you through a year of math. And so far, these 3 videos, in my mind, if my student by the end of 4th grade has mastered all of this stuff, and yes, there's going to be problem solving, and there's going to be, here's a budget, and things cost this amount of money, and can you have the party for $100? You can do fun stuff with. Someone made a comment on the first video that I'm not showing enough practical applications, and yes, there are things in the real world. You can get a stack of pennies or pasta, and how can we count them, and how can we split them up? And there's a lot of things you can do with the math to reinforce it and to motivate it. These aren't videos about how to make kids excited about math. These are videos about like what's going on. Is there other ways that we could think about the math to make the algorithms make sense? Okay, that's it for me for lesson number 3. Probably be 25 of these, adding up to over 12 hours, getting you from kindergarten to 11th grade. Not going to do calculus or pre-calculus.